Hi, I'm Jack Broadhead, presenting with Tyler Patton and Victor Alfaro on the construction of perfect pulses and their applications in RF communications. Perfect pulses have a lot of special properties that make them useful for communications, the most important of which is that there's no low frequency component depending on the number of transitions in the pulse, which we'll get into the math in a minute. So just a quick overview of this presentation. We'll define perfect pulses mathematically, then Tyler will get into some MATLAB code he worked on, which generates perfect pulses, which we can do Fourier transforms and stuff in the computer with. And then we'll get into a specific example using Manchester code, which shows some of the power of perfect pulses.
What is a perfect pulse? Shown here is a square wave pulse. It is centered at t equals 0 and has a duration of 1 second. It has transitions at -1/2 and 1/2. This pulse also happens to be a p0 perfect pulse, which is the lowest order perfect pulse. What makes this a p0 pulse is the fact that there are 0 internal transitions. The signal goes high and stays high until the end of the pulse. To give an example of a higher order perfect pulse, shown here is a p4. There are a total of 4 internal transitions. Look how the pulse is symmetric about its center. Notice how the location of the transitions line up with a semicircle with radially spaced lines. This interesting geometry is the result of how perfect pulses are created. So how do we create a perfect pulse? This formula shows how to generate the coefficients of a perfect pulse. A perfect pulse will have n plus 2 coefficients, so a p4 perfect pulse will have 6 coefficients. The coefficients belonging to a Pn perfect pulse describe the locations of the n transitions of the Pn pulse. Perfect pulses are unique due to their ability to remove lower frequency components. A P2 perfect pulse, for example, removes the DC and lowest frequency term from a standard square wave pulse. This results in a very interesting Fourier transform. A generic square wave pulse will have its peak at the center, while a perfect pulse will have peaks that are equally offset from the center. This is a very useful feature that will be explored later. Here's a quick rundown on how to generate a perfect pulse in MATLAB. The first step is to generate the coefficients of your perfect pulse. In this case, I'm doing calculations for a P4 pulse. The next step is to generate the time domain perfect pulse. This is done by summing together a bunch of rectangle functions that start and stop on the values of the coefficients for the perfect pulse with alternating amplitudes of 1 and -1. Then we take the Fourier transform and plot. So if I run this, you can see the 6 coefficients generated for the P4 perfect pulse. You can see the time domain representation of the perfect pulse and its Fourier transform in both linear and dB scale. Here's a P0 perfect pulse. There are 0 internal transitions, which means the Fourier transform is going to be centered around the carrier frequency. Here's a P1. There's 1 internal transition. Notice how the Fourier transform is shifted to the right slightly. A P2 gives an even more exaggerated shift to the right. So does a P5, a P10, and all the way up to a P20.
So, like we mentioned, there are a lot of applications for perfect pulses, one of the most important of which is backscatter communications. So this is a case where we, for whatever reason, don't want our data on the center carrier frequency. For instance, we might be borrowing the carrier from another transmitter that we don't control, so we know the frequency they're transmitting on, but we don't know the content exactly, and that carrier might not be clean because it might be a radio station. So if our transmitter transmits perfect pulses, we place a null at that other carrier frequency, and our data isn't stomped on by that other transmitter, but we're still transmitting using their power, which is really clever. Another instance is radar. So we might want to avoid jamming. Somebody else may have a jammer where they're transmitting really powerfully on our carrier frequency, assuming that we have data there. But if we use perfect pulses and our data isn't focused on that carrier, they're not actually blocking our data at all. Another example is RFID. These are tags which can transmit little amounts of data, and it's basically a backscatter communication technique. Another example is Manchester encoding, which I'll dive into now, which is a pretty common encoding technique used in normal circuitry and in RFID, which takes advantage of some of these perfect pulse advantages. So here is a pretty simple binary string we want to send. So we might send it with this simple way, we call them imperfect pulses or P0 pulses here. The data is encoded on the levels. So a 1 is a logic high and a 0 is a logic low. There are some problems with clocking, which I won't get into too much, but for instance, these two sequential ones, if our transmitter and receiver don't know in advance what the transmit frequency is, the receiver might think that's only 1 bit, it might be 2, or it might be a million bits, we don't know. So we have to either have an external clock signal, which requires another wire, that's not really ideal, or the transmitter and receiver have to agree on a frequency in advance, which still has some problems with phase locking. The bigger problem is that there's a DC component here, a really big DC component, which might not make it through an isolator, which we'll get into in a minute. Here's the same signal using perfect pulses. So in this case, they're P1 pulses. There's one transition per pulse, per bit in this case. So a falling edge here is a 1, and a rising edge is a 0. The nice thing here is that the data is encoded on the transitions, not the levels. So every single bit is guaranteed to have at least one edge, so it has clocking built in. We don't need an external clock, and the transmitter and receiver don't even need to agree on a frequency in advance. Within just a couple bits, the receiver can lock in and know what the transmitter is transmitting at. More importantly is that there's not a strong DC component here. Because there are transitions, we're guaranteed to always have some sort of high frequency component. So here's a pretty simple schematic transmitter with just a voltage source, a receiver, with the isolator I mentioned. So this is something that's used in Ethernet, where we don't want this line voltage directly coming into contact with our circuitry. So we use something as simple as a capacitor to isolate. However, this forms a high-pass filter with our internal resistance, which gives some challenges. So here is the imperfect pulses if we were to just send a bunch of binary 1s. Pretty fast, we can see here's the transmit in green and the receive voltage in red. Pretty fast, it drops to 0, which we expect through a capacitor, but it yields this signal pretty much unusable. Here's the same thing using Manchester code, though, because the data is encoded on the transitions, which are inherently very high frequency and have to make it through the isolator. We can always detect a transition pretty cleanly. So using the fact that perfect pulses don't have a DC component, we sort of get around this problem that normal pulses have. And of course, we can see that this is self-clocking, which is another advantage, but not focused on here. So this is just one example of one of the many applications in sort of a more classic circuit analysis way. There's a lot of other applications in RF, like we mentioned. So overall, perfect pulses have some really unique time and frequency domain features, which make them really useful in communication. In closing, we'd like to give a thanks to Professor Durgan for his resources and research into perfect pulses. This deep dive would not have been possible without them, and we probably would not have learned any of this. So thank you.